The next topic is Fourier transform. Is capable of decomposing a complicated waveform into a sequence of simpler elemental waves. More specifically, just like a Fourier series, weighted sum of sines and cosines. This is analogous to a wave representing a music chord. For example, one consists of a notes C, D, E can be expressed in terms of the properties of its basis notes. Further, if we graph these notes via the Fourier transform on a Fourier frequency versus intensity graph, there will be visible peaks corresponding to these music notes. An original function and its transformed counterpart are collectively known as Fourier transform pair. One of the most common uses of the Fourier transform is to find the frequency range of signals that changes over a time. And this form of signal processing is used in many places such as cryptography, signal processing, oceanography, speech patterns, communications and image recognition. Furthermore, Fourier transform can also provide to be a successful technique in solving differential equations also. Most important one is here the Fourier transform is applicable for periodic signals. In the case of Fourier series, we are able to apply for periodic signals, but Fourier transform is applicable for periodic signals. Then the Fourier transform can be given by the equation as Fourier transform of g of t, the signal in time domain, is equivalent to g of f in frequency domain, which is equivalent to integral minus infinite to infinite g of t e power minus j 2 pi f t dt. Fourier inverse Fourier transform is g of f, which is equivalent to g of t in time domain, is given as integral part of minus infinite to infinite g of f e power j 2 pi f t df. Some of the examples are given here. The pulse in a time domain going to be equivalent to sync function in a frequency domain by using Fourier transform pair. If it is not a symmetrical one, the magnitude and phase parts are going to be given like this. In a similar way, for discrete data, we can apply the discrete Fourier transform. The concept here in continuous time domain signal to a discrete domain can be obtained by simple switch case. Analog signal passed, this switch going to be opening and closing going to be at a regular intervals of time t. Then the samples are collected at which is equivalent to 1 by t. Then xa of t, analog signal in continuous time domain transformed into xn, which is equivalent to xa of nt. Continuous signal samples at regular intervals of t as n going on 1, 2, 3 up to so on. By this way we can collect at the end of this discrete time signal. Based on these discrete time signals, we can apply the Fourier transform. Analog signal represented by xa of t, which is equivalent to a cos 2 pi f t plus theta. Then at a time t equal to nt, we are going to collect the samples. That was shown in a t is the sampling time, 1 by fs is the sampling rate. So n by fs. Simply you can say, in place of t, if you substitute n by fs, you are able to convert it, transform the analog signal to discrete domain. Simple example given here. This is the sample data xn a cos omega n plus theta. Certain phase going to be happening here. Then from the previous explanation, we are going to have here the DFT expression is given x of 2 pi by nk. Analog frequency range going to be minus infinite to infinite, but digital frequency range going to be 2 pi, either minus pi 2 pi or 0 to 2 pi. So among these discrete frequency components, we are going to collect n samples with an index of k. So total digital frequency range divided into n samples, then each and every sample indexed by k, that is equivalent to summation n equal to 0 to n minus 1 xp of n e power minus j 2 pi by n kn inverse DFT. That was, it is in a here 2 pi by n k is an index used to represent discrete locations of a frequency, so that instead of having 2 pi by n, it's a common, then we can use it as k also. X of k equal to summation n equal to 0 to n minus 1 x of n e power minus j 2 pi by n kn. Then inverse d of t. How you can obtain the discrete time data from the discrete spectra? This was given by x of n equal to 1 by n summation k equal to 0 to n minus 1 x of 2 pi by n k e power j 2 pi kn by n, where n is varying from 0 to n minus 1. So this one is a DFT expression, this one is inverse DFT expression. By using this pair also, we can transform the discrete time domain data to discrete frequency representation. These are the standard formulas whatever we just discussed. Then here in the previous case also DFT, we are not able to get the spectral details at time representation. We have an idea about these are the frequency components, spectral details have the particular signal only. So to overcome this problem, we will move to short time Fourier transform. See, just this is a gray color, light in color one going to be the signal x of t, whatever you are going to get, that may be as radar signal processing, speech signal processing, or some other signal, biomedical signal processing. That signal going to be taken or observed over a particular time slot going to be fixed here. So we are going to have different time slots here. That was represented by this short time Fourier transform. Stft is a Fourier related transform used to determine the sinusoidal frequency and phase content of a local sections. This is the keyword of a signal as it changes over time. So for this local section, we are applying this window. Window is nothing but just over which you are going to apply the Fourier transform. So you selected this part and applied that Fourier transform. You selected this part, applied the Fourier transform. So by this way, different local sections are going to be applied for the Fourier transform. So that we call it as a short time. We are selecting this period going to be very short time Fourier transform. This is the general diagram. X of n is a discrete time you are going to apply here, and short time Fourier transform on discrete data also we are able to apply. Then this is nothing but transformation, phase details, and x n of 0. 0 at the slot or local time you applied this going to be happening here. Then the short time Fourier transform allows to perform time frequency analysis. It is used to generate representation that capture both local time and frequency content. By this way, whatever the Fourier series Fourier transform DFT, we missed that parameter, time parameter, we are able to have that details also. That means the local time and frequency content in the signal can be obtained by using this Fourier transform, which is going to be applied for a short time, not the entire time. Similarly to the Fourier transform, the short time Fourier transform still relies on a fixed basis functions. That means a fixed window. However, it uses fixed size, time shifted window function W of n to get a transformed of the signal and can be expressed as by this way. So xk of m indicates you kth local spectral details. Here m x n plus m indicates here incremental values. Suppose x of n going to be n samples we collected, x of n plus m will collect n plus 1th interval. By this way we are going to have some local time and frequency content, so that we can overcome the problem whatever we are facing in a Fourier series Fourier transform, discrete Fourier transform by using this short time Fourier transform. So what it means, however, the Stft has a better temporal and frequency localization, properties compared with the Fourier transform. However, since the product of temporal and frequency resolution is a constant, we are not varying that window size here. What is the problem? When you are not able to move the window size. Because of the classical Heisenberg's uncertainty principle, the generated features cannot achieve instantaneous localization of both time and frequency. In addition, due to using a fixed window length and fixed basis function, the short-time Fourier transform still cannot capture events with different durations or when the signal contains fast, sharp variations or events. Different durations are not possible by using short-time Fourier transform, and when the signal contains a fast variations, short-time Fourier transform not able to contain. For example, say this one. So, this is audio signal recorded through a smartphone or else whatever it may be recorded data it is. By just looking this, we have 1, 2, 3, 4 types of signal variations we are able to see through the time domain representation. One is a throat clearing, cough, sound and respiration. To process all these parts, each and everyone having its own duration. It's not equal duration. So, when you are applying Stft short time Fourier transform which is having fixed window size, then we may miss some of the instantaneous fast variations or some signals. That means if you fix a window for this period to this period, this period to this period, here you are losing the information relevant to cough. And you are fixing this, you are going to process a sound signal half. At this instance, if any fast variations are existing, not able to capture. This is a problem with the short time Fourier transform. Then overview about it. Short time Fourier transform exhibits a constant resolution at all times and frequencies. Short time Fourier transform is desirable in applying to unimodal, univariate signals wherein multiple component complexes do not exist, and moreover the signal artifacts and noise are very low. Short-time Fourier transform features might be used or need a threshold level using extracting the and fixing as a window size, or as a fixed window limits the amount of non-stationary characteristics to be extracted. This is the figure whatever we saw in a previous one. So, the spectrogram of audio signal is shown in a previous figure. In order to overcome the limitation of a short time Fourier transform, to get the fast variations, sudden variations at the end of the window, the wavelet transform is helpful. This is the problems whatever facing with other transformations. This can be overcome by using wavelet transform. So we will end up here the session.